Today we're going to continue our discussion on strengths of acids and bases, but we're also going to determine if solutions of salts are acidic, basic, or neutral. So last time we discussed anions as weak bases, and we said that the stronger the acid, the weaker the conjugate base. And our example there was hydrochloric acid, and its conjugate base is the chloride ion. And we can see that this is not a reversible reaction. So the chloride ion is not acting as a base, and in fact, an anion that is the conjugate base of a strong acid is pH neutral, because it's not going to act as an acid or a base. Now, we also said that an anion that is the conjugate base of a weak acid is basic. So we saw the example of hydrofluoric acid and its conjugate base, fluoride. And fluoride can act as a base and take a hydrogen from water to produce hydrofluoric acid. So if we had a solution of fluoride ions, it would be basic. Now we can also apply some of these concepts to cations. So cations as weak acids here, the stronger the base, the weaker the conjugate acid. So if we have a cation that is the counter ion of a strong base, that's going to be pH neutral. So for example, if we have NaOH in water, it's going to dissociate and produce a sodium ion and a hydroxide ion. And then the cation here is the counter ion of the strong base, sodium hydroxide, and it is pH neutral. It doesn't have an effect on the pH of the solution. Only the hydroxide ions do. Now, a cation that is the conjugate acid of a weak base is considered weakly acidic. So previously we saw that ammonia, NH3, reacts with water to produce ammonium ions and hydroxide ions. And we said that ammonia was a weak base, so this is a reversible process. Now, because it is a reversible process, ammonia's conjugate acid, the ammonium ion, can in fact act as an acid. It can react with water to produce ammonia and hydronium ions. So if we had a solution of ammonium ions, that solution would be acidic. Now, another example of cations that are acidic are small, highly charged metal ions. So these can also form weakly acidic solutions, and some good examples are aluminum and iron. So aluminum always has a 3+ charge, it's in group 3, and it has 3 valence electrons that it can lose. And then iron is a transition metal that can have variable charge. So in particular, the 3+ iron ion is acidic, because it's small and highly charged. Now, just to go into a little bit more detail about aluminum, the reason it can act as an acid, so aluminum 3+ can react with water, and this forms a hydrate. Now, that hydrate can actually go on to interact with another water molecule, and let me write in the states here. And you'll notice that in the first reaction I put a single arrow, and in the second reaction we actually have a reversible process. So in this reaction, the aluminum hydrate complex is going to act as an acid, Water is going to act as a base, and we're going to end up with aluminum bound to 5 water molecules and 1 hydroxide molecule. And then we're also going to form the hydronium ion. So this particular interaction with aluminum and water is producing acid. So this is an acidic solution. But in general, just know that aluminum 3+ and iron 3+ are both small, highly charged metal ions, and so they can form weakly acidic solutions. Now, what if we have a salt solution, and we want to determine if that solution is acidic, basic, or neutral? And just for argument's sake, let's say we don't have any pH indicator or an electrode handy. One way that we can determine if these salt solutions are acidic, basic, or neutral is by piecing apart the individual ions that are in the ionic compound, and then stepping through and figuring out, are these ions acidic, are they basic, or are they neutral? And we're going to use the same concepts that we were just going over. So let's start with sodium chloride. I'm going to change my marker color here. So if sodium chloride dissociates in solution, we end up with the sodium ion and the chloride ion. Now, we already said that if we have a cation of a strong base, that means that the cation is pH neutral. So remember from before, we looked at the reaction or the dissociation of sodium hydroxide, which is a strong base. And again, the cation of a strong base is pH neutral. It does not have an effect on the solution pH. And then the chloride ion, you might remember, comes from hydrochloric acid. So the chloride ion is the conjugate base of a strong acid. And remember that an anion that comes from a strong acid is also pH neutral. So it cannot act as a base or an acid. So because both of the ions in this compound are pH neutral in solution, that means that a sodium chloride solution is pH neutral. All right, now what about calcium nitrate? So we have a calcium ion and 2 nitrate ions, but we're just going to look at the single ions here. And calcium is the cation of another strong base, calcium hydroxide. And this is also why it's important to know the different strong acids and bases, because then you can identify whether their conjugate acids and bases are also strong, or, are pH neutral, or if they're also weak. So in this instance, because calcium is the cation of a strong base, it is pH neutral. And then nitrate is the anion of an acid, so it must be the anion of HNO3. So nitrate is the conjugate form of nitric acid. So nitric acid is one of our strong acids. Remember to review strong acids and bases if you're not quite there yet. So because nitrate is the anion of a strong acid, it is also pH neutral. And again, because both of the ions in this compound are pH neutral, that means we have an overall pH neutral solution. All right, and then finally we have potassium bromide. So potassium is similar to sodium. It is the cation of a strong base, in this instance potassium hydroxide. And that means that potassium is pH neutral. And then bromide is similar to chloride. It's the conjugate or counter ion to HBr, which is one of our strong acids. So because it's an anion of a strong acid, it is also pH neutral. So this overall solution is pH neutral. All right. So hopefully that made a little bit of sense, stepping through each of these different examples. And once you become more familiar with strong acids and strong bases versus weak acids and weak bases, this process will become easier as well. Now, what if we have salts in which the cation does not act as an acid, so it's pH neutral, but the anion acts as a base? That means we're going to end up with a basic solution. So we already stepped through some examples where we said that sodium ions, calcium ions, and potassium ions are pH neutral. So I'm just going to put a little indicator up here. A red circle means that we have a pH neutral cation. Now this time though, these pH neutral cations are bonded to anions that might not be pH neutral. So let's step through each of the anions. So in sodium fluoride, the anion is a fluoride ion. And this is the counter ion to hydrofluoric acid, which we saw earlier. Hydrofluoric acid, we said, was a weak acid. And that means that fluoride is a weak base. Now, because fluoride is a weak base, and sodium ions are pH neutral, that's going to create an overall basic solution. Now, what about calcium acetate? So the anion in this ionic compound is the acetate ion, and its counter ion is acetic acid. And acetic acid is a weak acid. So this is what's in vinegar. So that means that the acetate ion is a weak base. So if we have a solution of calcium acetate, calcium is pH neutral, acetate is basic, so we would have an overall basic solution. And then finally, we have potassium nitrite. We already said potassium is pH neutral. The nitrite ion is the counter ion to HNO2, which is nitrous acid. And nitrous acid is a weak acid. So that means that the nitrite ion is a weak base. And this solution, similar to the others, will also be basic. Okay, now our next example is a salt in which the cation acts as an acid and the anion does not act as a base, so it is pH neutral. And we're going to see that in this example we form an acidic solution. So our one example here is ammonium chloride. There are other examples, but I figured by this point you probably figured out our process. So we're just going to go over one example. So ammonium is our cation, and chloride is our anion. And the ammonium ion's counter ion is, or I guess counterpart in this case, is NH3. Ammonia. So we already said that ammonia is a weak base because remember most bases contain a nitrogen atom. And that means that the ammonium ion is a weak acid. Now earlier we said that the chloride ion is the conjugate or counter ion to hydrochloric acid, which is a strong acid, and the anion of a strong acid is pH neutral. So because we have a pH neutral anion and an acidic cation, this solution will be acidic. And your textbook has a few more examples of these types of solutions as well. Now, the last example is a salt in which the cation acts as an acid and the anion acts as a base. So this one is not quite as obvious, and we're going to have to compare the relative strengths of the acid cation and the basic anion. So in this example, we have the aluminum ion and the acetate ion. Now, I think there's a typo in the slides I posted. I think this says aluminum nitrate. Ignore that. We're going to focus on aluminum acetate. So we already said that small, highly charged metal ions act as acids. So we know that aluminum 3+ is acidic. And then in a previous example, we said that the acetate ion is basic, or weakly basic. So now we have a bit of competition here. Is the solution acidic? Is it basic? Is it neutral? We're going to use Ka and Kb values to determine the relative strengths of these ions. So the Ka value of the aluminum ion is 1 × 10⁻⁵. And then we don't have a Kb value listed for the acetate ion, so instead we're going to use the fact that Ka times Kb is equal to 1 × 10⁻⁴. And what we're going to do is solve for Kb. And in order to solve for Kb, we're going to plug in the Ka value for acetic acid, so the counterpart to acetate. Now that value, if we look it up in our textbook or in a table, is, let's see, 1.75 times 10⁻⁵. So the Kb value for acetate is 5.7 times 10⁻⁻⁻. So if we compare the Ka value to the Kb value, we can see that the Ka value is greater than the Kb value. So that means that this is an acidic solution. So again, the aluminum ion has a Ka value of 1 times 10 to the -5th. So it is very acidic. And then the acetate ion has a Kb value of 5.7 times 10 to the -10th. And remember that the smaller the Ka value, the weaker the acid, and then the smaller the Kb value, the weaker the base. So because we have a really small Kb value here, that means that the acetate ion isn't that strong of a base. In fact, it's a pretty weak base. So in a competition between our acid and our base, the acid wins out. So remember, the larger, oh, I don't know what I'm spelling there. So the larger the Ka value, the stronger the acid. And that's the same for the base. So the larger the Kb value, the stronger the base. So we can see again that acetate is a very, very weak base. So this table summarizes these different types of solutions. So for example, we have cations on the left and then anions up above. And let's say that you have salt, and let's say the cation is the conjugate acid of a weak base, and then the anion is the counter ion of a strong acid. That means that we're going to have an acidic solution. And then you can see that you can kind of follow along in this table. Let's say you had a counter ion of a strong base and the conjugate base of a weak acid. Your solution would be basic. So you can kind of go through and use this table as a guide to figure out whether something is acidic, basic, or neutral. And obviously on a quiz or an exam, I don't have a good way of proctoring you, so if you want to use this table during an exam or a quiz, go ahead, but I might give you some pretty tough problems to work on, so just keep that in mind. Okay, now let's work on worksheet problem 7. So in this problem, we're going to determine if each salt will form a solution that is acidic, basic, or pH neutral. And on the right-hand side, I included that chart from your textbook of strong, weak, and acids and bases. So that might be useful. And our two examples are K2CO3, so potassium carbonate, and then NH4ClO, which is ammonium hypochlorite. So if you want to pause the video and try this on your own first, go ahead. And then you can restart the video and we'll go over it together. Okay, so let's go over A, which is potassium carbonate. So our two ions are potassium and carbonate. And we said that potassium is the counter ion for a strong base, which is potassium hydroxide. So that means that this cation is pH neutral. And then carbonate, I'm going to go back a slide. Carbonate is right here on our chart, and its counter ion is bicarbonate, HCO3-. And that is a weak acid, and we can see that carbonate is a weak base. Okay, so we have something that is pH neutral and then something that is basic. So if you want, you can go back to this table. So we have again a counter ion of a strong base and then the conjugate base of a weak acid. So that tells us that we have a basic solution. I'm just going to erase this though before we go back. All right, so we have a basic solution. Now what about B, ammonium hypochlorite? So the two ions are the ammonium ion and then the hypochlorite ion. And we already said that the ammonium ion is coming from NH3, or it's the counter ion to NH3. And we said that NH3 is a weak base, which means that the ammonium ion is a weak acid. We can also see this on that chart. It's right above the carbonate and bicarbonate ions. Now, unfortunately, hypochlorite is not on that chart. However, if you look this up in, or if you look up the acid, which is hypochlorous acid, hypochlorous acid is, oh, where did my notes go? Oh, there it is. So hypochlorous acid is a weak acid. Sorry about that, I have papers everywhere. So the hypochlorite ion is a weak base. Okay, so this one's tricky again because we have an acid and a base. So we're going to have to compare Ka and Kb values. All right, now unfortunately, we don't have a Ka value for the ammonium ion listed in our table, in our textbook. So instead, we're going to use the Kb value of ammonia to solve for the Ka value of the ammonium ion. So the Ka value of the ammonium ion will be equal to 1 times 10 to the negative 14th divided by the Kb value of ammonia. So if you look up the Kb value of ammonia, that is equal to 1.76 times 10 to the negative 5th. So this will give us a Ka value of 5.7 times 10 to the negative 10th. Okay, and now for hypochlorite. So we don't have a Kb value handy for hypochlorite, so we'll have to solve for that using the Ka value of hypochlorous acid. Okay, so in your textbook, in the very back, again, is a list of Ka values. So we're going to plug in the Ka value of hypochlorous acid, which is 2.9 times 10 to the negative 8th. And once we do that calculation, we'll find that the Kb value of hypochlorite is 3.5 times 10 to the negative 7th. Okay, so now we're going to compare the Ka value of ammonium and the Kb value of hypochlorite. So which one is bigger? So you should have said the Kb value. And because the Kb value is greater than the Ka value, that means that this solution is basic. Okay, so we'll stop there today, but hopefully this helped a little bit with figuring out whether a solution is acidic, basic, or neutral when it's not quite as obvious. And I will see you in the next video.